So I want to tell you about work that is nearly complete, done with Kartik Prabhu and my current student, Gautam Satishchandran, which I hope will appear reasonably soon. We do have a nearly complete manuscript, but it needs a lot of editing, but shouldn't be that long. Okay, so many of you, but probably not all, are familiar with what the memory effect is. I'll review that. Most of you are not quantum people and undoubtedly have heard of infrared divergences in quantum field scattering, but that's what I want to tell you is that first, the infrared divergences are precisely the quantum manifestation of the memory effect, and then discuss, what one can and or should do about the infrared divergences in quantum field theory. So first, the memory effect. So if you have some, to just explain it first in physical terms, if we have some array of test particles, and we have some gravitational wave coming in normally, well, these particles will go into a sort of characteristic oscillation where, they will keep their area kind of fixed, but expand in one direction, contract in another, and then as the oscillation cycles continue, the cycle of oscillation continues, that will reverse. The interesting thing from what I'm going to talk about is that after the gravitational wave has passed, in quite generally, we're doing an asymptotically flat space-time and working to order 1 over r, these particles will return to rest with respect to each other, but they will not return to their original configuration. They will remain in some, sheared configuration like what I'm showing. Now, the kind of situation, that I want you to have in mind, and I apologize because I pirated this slide from another talk where I was in possibly higher dimensions. It's actually essential for the infrared divergence that we're in 4 dimensions here, but this illustrates that I want to consider a situation quite generally. We're going to consider an electromagnetic analog as well very shortly, where I have incoming, if we're doing this classically, particles or massive bodies. More generally, I'll want to consider some incoming massive field, actually. And in the quantum case, we're certainly considering incoming massive quantum field, but that can be given, the states can be given particle interpretations. And, this does whatever it does interaction, and there's some outgoing state. In the gravitational case, maybe you'd even form a black hole, and that would be one of the outgoing particles or whatever. This is really quite general. You also might be sending in some radiation from past null infinity. But what I want to emphasize here is the situation that we're considering. This detector, gravitational wave detector, is placed out here near null infinity. It's going to be observing non-trivial things at order 1 over r. And I'm going to assume that the radiation takes place over a finite extent. I don't mean a strictly finite extent, but the Bondi news is going to decay nicely as you go toward future timelike infinity, and it was nearly 0 as similarly decays as you go toward spatial infinity. And the precise, what I'm saying is not critically dependent on the precise rates of decay or whatever, but I certainly want the Bondi news to be L1, for example, and so on. Okay, so this memory effect, we can ask what the displacement of the relative displacement of 2 charged particles are relative to their compared with their initial displacement, that describes some linear map on the initial displacements, and this side, of course, is computed by just integrating the geodesic deviation equation, which will involve the Wald tensor. If there's no matter, there's no Ricci tensor. Let me assume that. Although that's not important either for what I'm saying. But the point that I'm getting here is that this memory tensor the Wald tensor will be non-vanishing at order 1 over r when you have radiation. And when you integrate it, it will generically be non-vanishing and give you some non-zero memory tensor, which at order 1 over r, I mean, well, it's, as I say, it's generically non-vanishing, but it also will be gauge invariant. I mean, so this is a completely meaningful quantity. Okay, well, if we choose some Bondi-like coordinates and I let h denote the deviation of the metric from a flat metric at order 1 over r in this asymptotically flat space-time, then in fact this memory tensor, well, again, at order 1 over r is what I'm considering here, and it'll only have angular, non-vanishing angular components, which in fact will be given by the integral of the Bondi news. I left off the du here that I'm integrating, over retarded times at null infinity. And that will be given in, some Bondi-like coordinates by the difference in the angular components of the metric between spatial infinity and future timelike infinity. Now, the situation is really completely mirrored by the situation in electromagnetism. And in fact, for the infrared divergences, I'm going to begin by discussing I'm going to mostly really discuss the electromagnetic case. So let me give you the electromagnetic analog of what I've just said here in a similar setup where now we may have charged particles coming in and emitting emission of electromagnetic radiation. So let me now let A mu be the vector potential at order 1 over r, and let EA be the angular components of the electric field at order 1 over r, which will be non-vanishing during a radiative era, just as the Bondi news is. So the analog definition, where I also left off the du here, I apologize, we're integrating over retarded times again at null infinity. That it will define the electromagnetic analog of memory, and that will similarly be given by the difference of the vector potential at future timelike infinity and it's at spatial infinity. If you want to measure this, you don't need as fancy an array, of test particles. It'll do perfectly well to take one charged particle and see if it gets a momentum kick in an angular direction. This electric field is giving the force on the particle, and if its integral is non-zero, it'll get a momentum kick. So that's the physical analog of memory in the electromagnetic case. Okay, so now the and we'll get to the metric in a second, but let's stick with the electromagnetic case. The A, of course, is not gauge invariant, and we're only concerned with the situation at order 1 over r. But if I take a gauge function that doesn't go to 0, but is in fact just so it's constant in r, and it's just a function of angles, that will actually preserve whatever asymptotic condition. Well, I'm imposing the asymptotic condition that the vector potential fall off like 1 over r, but that will be the case here. By the way, whenever I say 1 over r fall off, I mean 1 over r fall off of orthonormal frame type components, not coordinate components in angular coordinates or something. But these things are actually really should be referred to as symmetries rather than gauge, because they are not actually degeneracies of the symplectic form. And related to that, they have associated charges and fluxes that you can define. Well, the charges are easily defined at spatial infinity, but you can define them at null infinity too, and you can define fluxes associated with them. So the charge associated with a large gauge transformation of which is what they're usually referred to, is just given by the usual. So C here, I have in mind a cross section of null infinity. I'm defining the charge at some time on null infinity. So the usual expression for electric charge, you just take the, RT type component of F, the radial component of the electric field, and integrate it over a sphere. So you do the same thing here, but you get this weighting of the gauge function chi here. So if chi was 1, this would correspond to the ordinary electric charge. Now, what does this have to do with memory or whatever? Well, the memory is the difference of these A's in these cases. Now, the A at I naught is gauge dependent. I can do a large gauge transformation, but the difference between these two is gauge invariant, as is, it has to be because the memory is. And when you have memory, you're really saying that the A at early retarded times and the A at late retarded times differs by a large gauge transformation. But the fact that you have these charges and similar fluxes that will let you determine what the difference of charges are gives rise to a very important and useful formula for the memory. So this is really the formula that says the difference of charges is the integral of the fluxes, the flux associated with the charge. The flux has two terms, one of which, when you integrate over all U, just gives you the memory. So I've written that one on the left side. And then you also will get a flux contribution due to the flux of charge through null infinity. Now, usually one doesn't consider that because you can only get such a thing if you have massless charged fields, but I'll be wanting to consider that case. So this is the general formula. The charge at future timelike infinity, I should say, is completely determined by these. So that's the charge way up here at null infinity, but that is really just going to be the sum of the Coulomb type fields of these outgoing charged particles. Of course, these are all boosted Coulomb fields, so they have non-trivial angular dependence at order 1 over r that can give rise to this non-trivial angular dependence in the memory, in the vector potential in the memory. Okay, well, the situation in the gravitational case is exactly parallel. Again, we have these diffeos, the BMS transformations that preserve the asymptotic conditions on the metric, and in particular, we have super translations that do that, and the BMS transformations are symmetries in the same sense as I was using that term in the electromagnetic case. And in a similar manner, I'm not saying this is a totally straightforward story. That's actually something that Zupas and I looked at in detail 20 years ago. But you can define associated charges and fluxes to these super translation symmetries. You can do that at null infinity. At spatial infinity, the charges would be straightforward, but at null infinity, it's a little less obvious. In stationary eras, I mean, in parallel with what I had in the electromagnetic case, you now have an integral involving the Wald tensor weighted in with the super translation angular function. This is now the 1 over r cubed part of the Wald tensor. And this formula, there would be actually some additional news terms if you evaluated the charge in a non-stationary era. So again, memory can be thought of as corresponding to the fact that the HAB at early and late retarded times differs by a super translation. And finally, and I think most importantly, when you use the flux formula and integrate that over all scry to get the difference between the charge at future timelike infinity and spatial infinity, and now you get again a memory term, and I'll put that on the left side, you get this formula, which is exactly parallel to the electromagnetic formula, except, well, you've got an extra index and an extra derivative here. But this flux is now the Bondi flux that will come in. If you had matter, massless matter flowing out, there'd be some stress energy contribution from that as well. And once again, the charge that you'd assign, I mean, this is, well, partly, I mean, assumption, I mean, because you'd need, for it to be a theorem, you'd need to really have a theorem on the asymptotic behavior of this general scattering situation. But, you know, I think it's quite reasonable to assume that, well, you can associate a sort of charge with these outgoing massive particles, and that should match the charge that you get at future, at time-like infinity as you approach it along null infinity. I'll actually make a further remark in terms of, you know, proving rather than kind of assuming. But I'm going to assume this, well, I probably don't really need to make the assumptions about the charge at future time-like infinity for much of what I'm going to say, but I am going to make that assumption when needed. Okay, so now there's one further ingredient here before I turn to infrared divergences in the quantum case that will be very useful, which is what you might call conservation of charges at spatial infinity. So I've been talking about future null infinity, but I could, of course, have said exactly the same things at past null infinity. And I claim in the electromagnetic case, if I look at the charge, any charge associated with a large gauge transformation and go along future null infinity down toward taking a limit toward spatial infinity, and I do the same thing at past null infinity, but I use the antipodal map composed with the chi, which is very natural if you think of spatial infinity as a point. So I'm just sort of continuing along the same generator of this future and past light cone. These two charges should match up, or will match up under assumptions about, I mean, what I'm saying is nearly tautological, but under some, quote, suitable regularity conditions of the Maxwell field, you can ensure that they will match up. And in a similar way, you will match these charges in the gravitational case under basically the Ashtekar-Hansen conditions near spatial infinity, I think you actually need a slight strengthening of some of the conditions or conditions that they assume, but it's essentially Ashtekar-Hansen conditions. So in the 20th century, this, I think, would be a completely what can you do better than, I mean, these guys thought very carefully about, and, conditions that should hold near spatial infinity and null infinity. And what they're assuming is probably very reasonable, and that'll give you the equality of the charges, and you could make a similar statement about the electromagnetic fields. Now that we're in the 21st century and there really is a lot of mathematical power, since this is entirely a weak field, I mean, nonlinear, but weak field kind of statement, because we're only concerned with a neighborhood of spatial infinity, it really should be in range to prove this. Now, you might say, well, Christodoulou and Kleinerman must have proven it, or it must come out of their work, but in fact, it isn't it can't be obtained from what they've done, because they chose initial data that essentially required the metric to be Schwarzschild to 1 over r. And then, of course, they had all their function space conditions on the deviation from Schwarzschild at order 1 over r. But in this kind of scattering situation, well, if we had no incoming radiation, then near spatial infinity, we would have Coulomb-like fields dominating things at order 1 over r, but they're boosted Coulomb or Schwarzschild in the gravitational case, which is what I was talking about, like fields. So you would, in fact, have a dependence that is sort of Schwarzschild-like, but the 1 over r coefficients would be angle dependent. So it would be, I've talked briefly with Lydia, Abhay Ashtekar and I suggested this. In fact, it would really be nice to replace, this sort of asymptotic condition at order 1 over r. Choose whatever you want to need at, for the deviation of the metric from this kind of thing. But now the charges would be non-trivial. The charges are all 0 in with the Christodoulou-Kleinerman type conditions. And one ought to really be, I think it would be interesting to prove, well, I'm assuming that it's true, prove this, as one should in the 21st century with a, if you have this initial data, then these charges really will line up. Okay, that was a side comment, and now I'm ready, although we need the matching of charges for what I'm going to say later, now I'm ready to move into infrared divergences. And now the point is, as I've already said, memory is the difference between late and very early times of the 1 over r part of the metric. But the 1 over r part of the metric in 4 dimensions, and only in 4 dimensions, also is the radiation field, and that's what you would quantize for at least describing the out states. We don't know how to give a quantum theory of gravity itself, but we can, as Ashtekar emphasized 30 or 40 years ago, we can define an asymptotic out and similarly in quantum theory of gravity via the behavior of the 1 over r fields. So again, individually, these are gauge dependent. We might as well assume this is 0 near spatial infinity, but then this will be non-zero in the future. So, of course, the H may well have lots of wiggles and all that here, but it's going to go from 0 to something non-zero. Now, what happens if you take the Fourier transform of an HAB, these are the capital A and the capital B's are the only ones I care about here. They're the only ones that would have this be gauge invariant and have this displacement, and those are really what I'm ending up quantizing. If you take the Fourier transform of something that doesn't go back to 0, you can easily check you're going to get 1 over frequency behavior in the Fourier transform. Now, this is relevant when we come to quantum theory, because the way people would construct the usual Fock space of outgoing states, well, that would be based on a one-particle Hilbert space. The Fock space would be that you would construct from positive frequency data using this Klein-Gordon norm. Well, it's really inner product. I mean, this norm comes from an inner product. This norm itself comes from the symplectic product that you get. So this is all very natural. Okay, and this has Fourier transform squared, and it has an extra omega in it because you take a time derivative. You'll take a time derivative in the symplectic product. But if this goes like 1 over omega, you get a 1 over omega squared and an omega here. So this norm, the Klein-Gordon norm of any state with memory, is not going to live in the usual Fock space. It is not, any one particle state of that sort is not going to be in the usual one particle Hilbert space. Now, there's nothing wrong with these states. They just have memory. And as I've just explained, they unavoidably are going to occur in any kind of scattering. But if you try to stick what you get as the out state into the usual Fock space, you're going to get a divergence, an infinity in expressing that state. So it might be worth making comment, because I think people have undoubtedly heard of both infrared that I just mentioned and ultraviolet divergences, and it'd be good for me to say a few words about what they are. So, of course, quantum fields are observables, so they would be represented as operators in quantum theory, but it's the operator sort of assumes you already have a Hilbert space, and the whole point here is that you don't have an obvious Hilbert space. This usual Fock space in particular is not going to work for all states you might be interested in. So it's actually much healthier to think of these things as elements of an abstract algebra that you get by, taking the free algebra generated by all your operator observables and factoring by any relations like commutation relations and so on that you might have. And then these abstract objects could get represented as operators in some Hilbert space representation of the algebra. If you don't have a Hilbert space, as I'm certainly suggesting that be much healthier not to require that you do in the first place, there's a perfectly good definition of states as just linear maps on the algebra. So linear maps are really just correlation functions, because the elements of the algebra are these products of fields, and this gives you then fields at the various x's, and this gives you then a number that could be interpreted as the expectation value of that quantity. But they have to be, they're not any linear functions, they have to be positive functions, any element of the algebra that's of this positive type, they have to give you a positive number. So this may sound weird, but this really nice and really simple GNS construction shows you that if you're given this algebra and given any state, you can in fact construct a Hilbert space representation of the theory where your state corresponds to a vector in that Hilbert space. So the remarkable thing about quantum fields, and the very deep thing about quantum fields, is that they are not defined at every x, but they're actually distributional. And that gives rise to serious problems trying to define, because you're going to want to look at nonlinear things in your quantum fields, but nonlinear functions of distributions are not well defined. And you really need to, this is something you really have to address, making up new rules for how to take products of distributions. You can't legally just take the product of these, you won't get the right wavefront set conditions or whatever, trying to take the product of distributions. You really have to do subtractions of things and so on to define them. This is, of course, what, most of what is being done in quantum field texts is related to, and this can be done in linear quantum field theory, which then enables you to do perturbation theory for nonlinear fields, but that one can't do much more than that. The infrared divergences are not serious. They arise from trying to stick the state in a Hilbert space representation in which it doesn't belong. So these are more like real singularities that you really have to work at to deal with. These are a little bit more like coordinate singularities, and I'll develop that. So what do people do given that you're going to get these infrared divergences? Well, originally, it was referred to as infrared back in the 30s as an infrared catastrophe or something, but it's pretty clear it's not too serious. What people normally do is, well, if you take your state and put in some infrared cutoff, then you can stick it in as a legitimate state in the Fock space. You can then calculate things like what people call inclusive cross sections, where you sum overall, you don't just calculate some process that you're interested in, but you calculate that process together with arbitrary soft photons. And then when you've calculated your cross section, you can then safely remove the infrared cutoff. And now if you're just interested in getting answers for CERN, this is perfectly fine. But from a fundamental point of view, it's really unsatisfactory. I mean, and particularly if you want to take some view that the S matrix is some fundamental thing, because you don't have the S matrix, you'd like to go from the in to the out Hilbert space, but you don't even have these Hilbert spaces. It's a little hard to say what you're doing. Furthermore, if you're only interested in what the types of things CERN measures, this is fine, but the memory is a perfectly good observable, and it will be entangled with other observables, and you might want to calculate that, and you can't possibly do that with this kind of truncation. So the states with memory, as I've said, are perfectly legitimate states. And in fact, you can find nice Hilbert space representations that have these states by just taking the usual Fock representation, but redefining the field operator by shifting it by a multiple of the identity, where that multiple is some classical field with the memory that you want. And now when you calculate anything, all of the states in this new representation will have this memory. Now, this will give you a unitarily inequivalent representation of the quantum field, but you've got nice Hilbert spaces to incorporate all memories. The problem now is, what do you take for the in and out Hilbert spaces? Well, you could take the direct sum over all memories of these representations of these memory Fock spaces. That's a colossal Hilbert space, because memory is some tensor function, arbitrary. Well, not arbitrary in its tensor behavior, but arbitrary in its function behavior on a two-sphere. So that's a lot of Hilbert spaces that you're direct summing over. And that still won't work, because if you start with an in state of definite memory, your out state clearly won't be in this direct sum. You might try direct integrals. Let me not, since I realize I'm running a little late on this. We're convinced that that doesn't work either. But remarkably, in massive quantum electrodynamics, there is a really neat construction of Kulish and Fadeev that goes back to the 1960s that will work to give you a nice in and out Hilbert space that maps into each other. Now, this is certainly not how they would have described their construction, but I'm virtually certain that this is, I think certain that this agrees, this corresponds to their construction. So that uses the fact that these large gauge charges are conserved. So you could work in a section of definite charges at spatial infinity. But the charges are not invariant under rotations and Lorentz boosts unless you go to the sector of vanishing charges. So if you want your in and out Hilbert spaces to have Poincare group action, you really need to go to the sector of vanishing charges. Now, that is a little inconvenient. You might want to consider scattering of two electrons. Well, if you wanted to do that, you'd have to put two positrons behind the moon, is the usual terminology, and to get to this vanishing charge sector. Well, that'll give you vanishing electric charge, but you need vanishing of all the large gauge charges. But that's where Kulish and Fadeev have this neat idea. So incoming states of definite momentum, well, they're not really proper states, but they are eigenstates of the charges at past timelike infinity. If you match that properly with the memory representation corresponding to that charge, any photon state in that memory representation, that will give you zero charge at spatial infinity. So this is a means of constructing a separable Hilbert space. When you direct integrate over the p's appropriately, and direct sum over the number of them, you'll get a Fock space, but where the incoming particles will be paired with photons in the needed memory representation. And this is what people call, I've wondered this for decades, this is what people mean when they talk about dressing electrons in a soft photon cloud. Okay, anyway, that will give you a Hilbert space. It's a little funny that you're only allowed to include incoming states that have incoming memory of the photons matched perfectly with the electrons and positrons and so on. But that it gives you enough states to, do scattering, and it gives you nice in and out Hilbert spaces. So the points I wanted to mention is that this doesn't, and I'll mention that very quickly since I'm really already out of time, but I'll take, if I may, 2 more minutes to give you a couple of punchlines. This idea fails pretty badly in massless quantum electrodynamics. You can again take these incoming momentum eigenstates of the charged particles, which are now null, and now they will contribute memory through their charged particle flux rather than their charges. But you can again try to pair that with memory of the incoming photons, and you can do that. But the problem is that this charge integral, charge fluxing, is angularly singular. This is related to what people call collinear divergences when they're doing these calculations. But that means that this memory that you need to pair has to have singular angular behavior. So if you're just trying to do a kludge where you're going to get the cross sections, that only really means you've got to put in some extra angular cutoff and so on, and then take limits after you've gotten your inclusive cross sections. But if you're trying to get a Hilbert space, all of the states are going to be unphysical because they're all going to have these angular singularities, and this is not a decent Hilbert space. Things are much worse in gravity. You, well, would have the same problems, but you want to go to a sector of vanishing charges. Well, you need to go to a sector of vanishing for momentum to do that in particular. That isn't going to give you a lot of states to deal with for scattering. So you can't do that, and you can't even get reasonable states with eigenstates of supertranslation charges that are eigenvalue non-zero. But you can also see the problem in that the particles that you're dressing with here are the same particles as are giving the flux. So if you have some incoming state that you're going to dress, well, you've got to now dress also that the dressing is going to contribute to memory, and you're going to have to dress that to kind of get rid of that, et cetera. I mean, there's just no construction in hand that will give you anything reasonable for states. So the point of view that I would, that I strongly take on this is I would view Hilbert spaces of states, or really Hilbert space representations, as very much like coordinate patches on a manifold. Well, don't push this too far. In the Hilbert space patches, there aren't overlap regions, and it's more like a non-paracompact manifold where you really got zillions and zillions of Hilbert space representations. But you should think of the state as being defined by its correlation functions. If you are given a state, you can put it in a nice Hilbert space, just like if I give you a point in any manifold, you can put it in some coordinate patch. But there's no reason why you should be trying to cover all states of physical interest in one separable Hilbert space representation. Certainly not any more than you should demand that you can cover all points simultaneously in a manifold with one coordinate patch. So a much more reasonable way, I think, of doing quantum scattering theory is, again, we take any in-state we want defined by its correlation functions. We use the same sort of LSZ perturbative methods as done in usual S-matrix calculations, but now instead of calculating out states, we calculate out correlation functions, which is what defines the out states. And we don't, unless we're asked to, try to put these states in any particular Hilbert space. So I have not seen anyone do this. We've only thought about this a little bit. It would be really quite interesting to develop scattering theory. I apologize for running over by about 5 minutes, but I have conveyed to you as best as I can how the memory effect gives rise to very interesting infrared issues in quantum field theory. And, I think it's quite of interest to try to figure out how to deal with those issues at a fundamental level. So thank you very much.